Welcome to this 8th lecture on calculus of variations. Till now, what we have done is we have seen what is the variation of a functional. We have seen that if a functional is differentiable, then we have seen that what is the variation of that differentiable function, what is the definition, and we have also proved that this variation is actually unique. And then we have seen that there is a difference between there is something called strong minima and maxima and weak minima and maxima, and we have seen that every strong extremum is a weak extremum, but the converse is not true. We have seen an example of an extremum which is a weak extremum but not a strong extremum. So where we are heading is we are heading like now towards the famous Euler's equation for finding finding extremum extrema of functionals. Okay, this is our aim now. We want to derive the Euler's equation, okay, for finding extrema of functional. That is a necessary condition for extrema of functional. We wanted to derive a condition for obtaining the maximum and minimum value of the functional, and that condition is Euler's equation. So we are moving towards that. We are like 5 steps away from this equation, from the derivation of this equation. So these 5 steps are one theorem and 4 lemmas. So let us try to move ahead. So the first theorem I'll prove is we'll prove that we have this functional j of y. Okay, we will prove that if this functional j of y has an extremum value at y tilde, then necessary condition for this functional to have an extremum at y tilde is that the variation of the functional should be 0 for all admissible functions h. We know that this variation at y tilde, what is this variation at y tilde? This is the value of the functional at y tilde or y hat, whatever you want to call it, minus the value of the functional at y hat. Okay, so we know that this thing will depend on this y hat and h. What is h? H is all possible increments which you can do. Okay, these are all possible admissible increments. So we are going to prove that if we have a functional which is differentiable, then the necessary condition for this functional to have an extremum at y tilde, at some functional y tilde, is that the variation of the functional should be 0 for all admissible increments. Okay, and this is a condition for actually weak maxima. We will see in the proof that this is a condition for weak maxima or weak extrema. Okay, but we don't have to specify it, that we will see how. So this is a theorem that a necessary condition for a differentiable functional jy to have an extremum for y is equal to y tilde is that the variation should vanish for y is equal to y tilde. That is, we should have that variation of the functional is equal to 0. Vanish means we know that the variation of the functional is a function of functions. So it should be 0 for all the admissible inputs. Okay. And you should also note that I did not write here any strong or weak extrema. I'll explain. But what we will prove is for weak extrema. Okay. But we don't have to write it here. We'll see why. Okay. So this is the theorem we are going to prove. I'm sorry. Okay, let us try to prove that theorem. Without loss of generality, you can assume that we have seen that we are saying that j of y assumes an extreme value at y tilde. So that extreme value can be a minima or a maxima. So without loss of generality, we can always assume that this is a minimum value. Okay, you can assume a maximum value as well. Then you have to just reverse the steps. You have to modify steps a little. So we are assuming that our functional assumes a minimum value at y tilde. So what does that mean? It means that there is a neighborhood of y tilde. It means that there is a neighborhood of y tilde such that we have this j of y tilde plus h minus j of y tilde is greater than equal to 0. Okay, actually this is hat. I'm confusing, so it's like I should call it y hat. Tilde is like this. Okay, hat is like this, so I should call it as y hat. So this is the definition of this functional having a minimum value at y hat. So we have a neighborhood of y hat such that this thing is greater than equal to 0, right? And this neighborhood, we have already seen that this neighborhood can be in the sense of 0 norm. Okay, in that case it will be a strong extrema, and it can be in the sense of 1 norm, and in that case it will be a weak extrema. Okay, okay, this is one point. This is one point. Now let us see by the definition of variation of the functional, we have this thing. We know that if j is a differentiable functional, then we have this change in the value of j is equal to variation in j plus epsilon times norm of h, where epsilon goes to 0 as norm of h goes to 0. This is the definition of variation. Okay, okay. So from here, this is our first point, this is our second point. Now see, if you are saying that this epsilon is going to 0 as norm of h going to 0, it means that for very small norm of h, if I choose h such that norm of h is very small, and in that case epsilon is going to be small, so in that case I have these two quantities, they will have same sign. Okay, these two quantities differ by a very small thing, and if I choose that very small thing wisely, then I can have these two quantities having the same sign. Okay, thus for sufficiently small h, okay, and this how small we have to choose, that will define a neighborhood of y hat. You know that what we are doing is we had this y hat, we are increasing it by h. Okay, so basically these are the functions in the neighborhood of y hat. Okay, these are the functions in the neighborhood of y hat. So you are choosing a sufficiently small norm of h, and that how you are choosing that will define a neighborhood of y hat, and we call that neighborhood as n. Okay, so now we know that in this neighborhood of neighborhood n, this change in the value of the functional and the variation of the functional, they have same signs. Okay, in the neighborhood of n, neighborhood of y hat, which we are calling as n. This is our third point. Okay, okay. And what we want to prove is that this variation is 0 for all admissible function. Okay, so that is the uh, conclusion of our theorem. That is what we want to prove. So we will go by our usual weapon, that is by contradiction. Suppose this is not true. Suppose this is not true. Suppose this is not 0 for all the admissible functions in which can be input. That is for all admissible h. So it means that there exists some admissible function h naught for which this variation is not equal to 0. Okay, so we assume that the statement is not true, therefore there exists some admissible function h naught for which this variation is not equal to 0. This is what we are assuming. Okay, now try to do one thing. We had this neighborhood n of y hat. Okay, we have seen up to now. Now for this particular step, what I am doing is, we had this neighborhood n of y hat. I am choosing in this neighborhood n functions of this form. Okay, in this neighborhood n of y hat, I am choosing functions of this form y hat plus alpha h naught, where alpha is positive and it is very small. Okay, it can be y plus minus. Okay, and note that these functions are close to y hat in one norm only. You can prove this. Okay, these functions are close to y hat in one norm. So it means that the neighborhood we are considering, or we have to consider, it should be in the sense of one norm. Okay, for the next steps. Up to now there was no problem. Up to this step there was no problem. Okay, but for the next step, I am choosing the functions of the form y hat plus alpha h naught in in the neighborhood n. I am saying that these functions are in the neighborhood n, and these functions are close to y hat only in one norm. So I am assuming that my neighborhood n is in one norm. Okay, so it means that everything we are talking about is about strong extrema. So here, in a neighborhood of y till y hat, I am saying, so I am saying that here I am choosing a neighborhood which is in the sense of one norm. So everything I am doing from now onwards is for strong, for weak extrema, not strong. Okay, because I am considering neighborhood in one norm. Okay, so okay, so I'm choosing a function y hat plus alpha h naught. Okay, and for this particular function y hat plus alpha h naught, what will be my variation? Variation will be a function. I have this. This is the increment. Instead of h, we have the increment alpha h naught. So we have, just a minute. Okay, so we can have like this. We have delta j y. Sorry, excuse me. So we have this j at y hat minus alpha h naught minus j at y hat. Okay, so this will be equal to increment, variation j. What is your h? H is minus alpha h naught. Okay, so see at the variation at minus alpha h naught. Because this is linear, because this variation is linear, so we can take the negative sign out. So we have this quantity is equal to minus variation computed at alpha h naught. Okay, so also you have to see that this function y hat plus alpha h naught as well as y hat minus alpha h naught, both are in n. Okay, both are close to y hat. And for one, for if we choose this function, then the variation is this. Okay, and if we choose this function, then the variation is without negative sign. Okay, so it means that, and also if this is positive, if this variation delta j alpha h naught is positive, then it means that this is negative because of this negative sign. And if this is negative, then this is positive, right? So what we have seen is, we have these two functions, both these are in the neighborhood of y hat. We have these two functions in the neighborhood of y hat, and variation computed at one of these functions is positive, and variation computed at one of these functions is negative. Okay, okay, so let us move to next now. Okay, so what we have seen is that this variation can have any sign in neighborhood n. Okay, now also we have seen that in this particular neighborhood n, this increment in functional and variation of the functional have same sign. So it means that this increment can have same, any sign, positive or negative, in this neighborhood n. But this is a contradiction, because we had seen that we because y hat is minimum. So by definition, del of j h is greater than equal to 0 for all h admissible, right? This is the definition of, when you say that this functional admits a minimum value at y hat. And but you, by contradiction, you have reached at a place where you are saying that this thing can have any value, positive or negative, in this neighborhood n. But this is a contradiction, so it means that our supposition is wrong, and del of j of h is equal to 0 for all h admissible. Okay, so this is a condition, this is a condition for the functional to have a strong, sorry, not strong, I'm sorry, for having a strong extremum value, for having a weak extremum value at y hat. Okay, so this is a condition, this is a necessary condition, okay, for a functional to have a weak extremum at y hat. Okay, so but as every uh, strong extremum is also a weak extremum, therefore any necessary condition for weak extremum is also for strong extremum. Okay, so there is no need to write it explicitly that this condition is a necessary condition for weak extremum. Okay, because every strong extremum is a weak extremum, so every necessary condition for a weak extremum is also a necessary condition for strong extremum. So we have proved that for this functional j y, which is differentiable, for this functional to have an extreme value at y hat, the necessary condition is that variation of the functional should be 0. Variation of the functional should be 0 at this y hat for all admissible increments h. Okay, this is the necessary condition for the functional to have an extremum. Now we are four lemmas away from deriving our famous Euler's equation that we will do in next video. Thank you.